Hey, what's up, guys? This is Chung here. So tonight, let's take a look at this week's weekly contest, 1,594 maximum non-negative product in the matrix. I think this is a good problem, you know. Basically, okay, so you're given like a 2D matrix and with like any numbers, basically any could be zero, it could be one, or it could be positive, and so and you start with the top left corners and you end with the bottom down, the bottom right corner. And you're only allowed to move either going down or going to the right. And it asks you to return the maximum products. Okay. And if the maximum product is negative, you return -1. Also, in the end, you do a modular by this number here because the product is going to be a huge number. Okay, cool. So, mm, I mean, if you follow the like this uh follow this like the problem descriptions, you basically if you try to use a DFS, basically every time you have two options, right? And then basically every time you have two options, you're gonna have like the 2 to the power of what? 2 to the power of rows plus column, okay? Because uh you need rows plus columns number of steps to move from the start to the end, right? And every place you have two options, so the total time complexity is going to be 2 to the power of row plus column. With this kind of like input size, most likely this one will basically will like TLE. I mean, even though you can do a simple like branch cuttings by maybe every time you see a zero here, right, you can just stop that branch because you know by the time we see a zero, we know, I mean, that branch will definitely have a zero. Okay, so basically we can just update the final answer with a zero. But still, right, but the worst case scenario is still going to be a 2 to the power of our rows plus columns. So we need a better solution. I mean, a better solution is the DP. Okay. I mean, if you guys still remember, I think a few days ago I uploaded videos about the how to get the maximum numbers, the maximum products of a 1D array. Okay, 1D array, right? So let's 3, 2, 0, -1, -5, 2. Okay, I think this problem is similar to that problem. You know, if you guys still remember, what did we do in that problem is we maintain like a biggest number at each of the positions here. We maintain like the biggest number and the smallest number, right? And then every time we just try to maintain those two those smallest and biggest numbers at each positions, right? And then we just keep going, and by the end, the maximum number, the biggest number, will be our final answer. Okay. So this problem is the same thing. Basically, instead of 1D, we have 2D here. So what does 2D means? 2D means, let's say, for example, at this place here. Okay. Basically, when it means that we have two options to get to the current position, because for this one, right? For the 1D, we only have one way to get to this one, just to get this one from the left. Okay. But here, besides to the left, we have another options coming from above us. Okay, so yeah, that's basically it is. Basically, besides the minimum and max value coming from the left, we also need to consider the minimum and max value coming from top. Okay, that's it. So basically, in that DP array here, so we're gonna maintain like two values, right? The maximum and minimum value. Okay, and I think one things we might need to be careful here is that most of the time, when we have a DP like uh, I, J, okay, equals to DP uh, like I minus one or J minus one, something like this. We usually try to pad. We usually try to pre-process this I minus one, J minus one, so that the when we do the for loop, the loop for the DP here, it will not go out of the boundaries. Hmm. But for this problem, right? Let's say this zero minus one. Let's say we have a minus two here. Okay, minus one, minus two, minus three, minus two, minus three, minus three. Okay, for this minus three here, it's obvious we have two options, right? Here, this one and this one. But for the minus two here, we have a minus one coming to minus two. But how about here, right? I mean, if we're trying to use that I minus one dp I minus one for this element here, we then we have to somehow pre-process the value for this dp I minus one here. Okay, dp I minus one j here. But what value we should put it in here? Let's say, right? Can we put 0, 0? Probably not, because we're doing like the product, right? I mean, by doing the product, we might change the minimum or the max value of this one. Because for example here, right? So minus one and minus one, the so I mean the minimum and the max value for this position is minus one and minus one, okay? And for this one is two and two, right? Because we only have one options here, right? That's why we have a by multiply by the minus two here, the minimum and the max value they're both like two here. But if we are like default like pre-process this this value here, I mean, can we do a 0, 0? Probably not. If we do a 0, I mean the minimum value instead of 2 will become to 0 in this case, right? Then how about the 1 and 1? Can we do 1 1 here? No, right? I mean, if we do 1 1 and 1 here, okay, then 1 multiply times minus 2 will be minus 2 minus 2. In this case, the minimum value will, instead of 2 here, will become to minus 2 here. So ideally, right? Ideally, so what's ideally this one should be the same as the as a left one. Then we can be sure that, I mean, we can be sure that this this like non-exist. This virtual node will not affect our final answer. Okay, that's one of the a tricky thing for this one. Basically, for this problem, we should not pre-process this I minus one thing. Okay, which means we need to uh, handle this case on the separately in the for loop, instead of relying on the pre-processed result, because this one we cannot simply pre-process default values in advance for all the values here. Okay, cool. So with that being said, let me quickly implement this problem here. Basically, we have a length grid. Okay, we have n equals to length grid 0. Okay, and then we also need a mod here. Okay, 10 to the power of 9 plus 7. Okay, and now we have a dp here, right? So like I said, since I'm not going to to pre-process that, so which means I'm going to just use the original size. Okay, I'm not going to do a n minus one, n plus one, and n plus one. Okay, so for I in range m and for j in range n. Okay. Okay. The number is this I and j. So I'm going to define like current max equals current minimum equals to 0. So, and basically if the I is 0 and j is 0, okay. Uh, so the first one, well, basically that's the first case. Basically the current max equals to current minimum equals to number, okay. That's the first case. Else if I equals to 0, right? So this means that, I mean, uh, this means that the current max equals to what? Equals to the max of the dp what? The I and j minus 1. Okay, because we're only relying on this one here. Okay, and times number. Okay, and then I'm gonna copy and paste here. 0 and 1. Okay. So 0 means I mean, we're gonna, so this one, the first one is the max number, and the second one is the minimum number. So basically, we're just doing, use the current number to multiply both the minimum and max numbers and get the max one, and same thing for the minimum one, okay? Okay, so that's the I equals to 0 case. And same thing for the j, right? When the j is equal to 0, we're gonna have this, okay? Right, so, okay, same thing for this. Oops. Same thing for this, okay? 1. And else, here. So in this case, we're gonna have like uh, two sets of the maximum and minimum. I mean, we can do a max of the max, minimum of the minimum, or we can just put everything into this max here. Okay, or we can just do this. Okay, I mean, this is what I mean here. I mean, we do this. Okay, and we do this. Okay, basically we just multiply with four numbers, basically with the two max from the two directions and the two minimum from the two directions, and then we do a maximum among all of them. Okay, maybe there's a better way of doing this, but I just I just use this like the easiest way of things here. Okay, now we have dp, right? So now we have dpi j equals to what? Current max and current minimum. Okay, so now the answer is what? The answer is like the dp n minus 1, n minus 1, 0, because the max one is the answer we need. So, but I'm gonna do a simple check here. Like I said, we need to do a return to minus 1 if the answer is smaller than 0. Okay, else what? Else we do a answer mod by the mod here, right? I think this should work. Should just work. Let's try to run the code. Index out of range. IJ. Oh, I think here. Sorry. Yeah. Okay, cool. Submit. All right, cool. So it's accepted. It's a I think it's an interesting like DP problem. As long as you can think you know that basically every time when you guys see next time when you guys see like it asks you to find the maximum product among either the negative or positive numbers. The first thing you guys need to know is that you need to maintain two values basically. The max for each of the state here, you need to maintain the maximum value and the minimum value so that later on you can use the minimum and max value to get the new minimum and max value. The only difference for this one is that it's a 2D it's a 2D grid here, which means that you might have two options, basically two sets of the minimum and the maximum. So you just need to consider all the possible possibilities, and basically you get the maximum among those two sets of minimum and maximum. Okay, and in the end, you just have this. You just have this one, the maximum as the final answer here. Cool. And yeah, I think in terms of the space and time complexity, it's obvious, right? Time complexity is m times n. Okay, and space is also m times n here. Yeah, since we need like both the left and the top values, right? We can't. I don't think we can compress the space complexity in this case. Yeah, we have to maintain a history of that. Yeah, but anyway, that's not that important here. Okay, cool guys. I think that's pretty much it is I want to talk about for this problem. And thank you so much for watching the videos, guys. Stay tuned. See you guys soon. Bye bye.